Okay, specific heat. We are defining specific heat. Specific heat is the energy required for 1 kg of the solid to increase its temperature by 1 Kelvin. And if you plot a graph of Cv versus the temperature, what we expect it to be same. But if you see for different solids, for different materials, the graph is like this. Say this is for iron, then for silver it is like this, for aluminium it is like this, the curves are different. That shows they are changing at a very low temperature. They are drastically falling towards zero value, and at higher temperature it is almost the same for all the metals. Right? The value is same at higher temperature for all the materials, and that value is equal to 3 times R. And R, you know, this value at higher temperature equal to 3R, and this is also equal to 3N into K. What is N? N is Avogadro number, K is Boltzmann constant, and if you multiply this appears to be the same value. Now you have to explain this. Why? This is all solids will have same value at higher temperature. Right? Classically, whenever an incident happens, we try to explain it classically. Right? We apply classical theory to explain that phenomenon. If not, we go to the quantum mechanics. First, classically, Dulong and Pitte Pitte's law. Dulong and Pitte's law. He used classical theory to explain the specific heat of solids, and he has to also say why it is drastically falls to zero at higher temperature, why it is suddenly falling to zero at lower temperature, and why it is constant at higher temperature. That was the problem. And we are addressing that with classical theory. This is classical theory. Classically, he says there is a vibration, lattice vibration, and there are two types of energy distribution. Whenever you supply energy to a solid, the energy is utilized in two ways. This is for atoms, right? Atoms are in a array. Array means lines in different planes, and we call these lines of atoms as a lattice. Okay, and they are different. Whenever you supply, they start vibrating, and this energy that heat energy that you give to the solid is utilized in bringing the vibration of the lattices. The lattices start by taking that energy, they start increasing their vibration about their mean position. As I said, if they are going 1 centimeter vibration, now they start going by taking the 2 centimeters or 3 centimeters. Like that, they are go on increasing their amplitude of vibration, and that is called lattice vibration. So there is a contribution of lattice vibration. Whenever it is losing energy, the lattice amplitude goes on decreases 5, 4, 3, 2. And there is another energy involvement. Means the energy that you supply is also used to increase the energy of the electrons. Because usually what happens? The atoms in the solids usually taken metals, they are ions. Why they are ions? they readily, all metals readily gives out their electrons. The valence electrons will come out very easily and they become free electrons. If they are sitting on last orbit, those are called valence electrons. They come out of the last orbit, then they start freely wandering. If they are bound to the atom, they are called valence electrons. If they are come out of that atom, then they start freely wandering, and those are called free electrons. So when atom comes out, when electron comes out of the atom, what happens for the atom? It becomes positively charged because it has lost a negative electron. So for that reason, usually in lattice, we mark the lattice atoms as ions, positive ions, because they lost their electrons. So whenever you give energy to this energy is bringing the vibration of the lattice, and also it is increasing the energy of the electrons. So the total heat is used in two ways: in bringing lattice vibration and in bringing the energy, increasing the energy of the electrons. So whenever it loses energy, it is same. While increasing you are supplying, while decreasing it is giving out. That's all. The value is same. Specifically, you can define it is the energy to be supplied for 1 kg of the substance to rise the temperature by 1 Kelvin. Similarly, you can define like this: it is the energy given out by the 1 kg of the substance when it is losing 1 Kelvin temperature. That too. Again, if you are supplying, temperature increase. If it is giving out, temperature decrease. So there is a contribution is coming. The heat, if it is giving out heat is coming by the electrons are losing their energy and giving out heat. And the lattice is decreasing its amplitude, its vibration, and giving out heat. So heat, if you give the increased vibration, the electrons start moving with greater energy. If it is giving out, the electrons are slowing down and lattice vibrations are coming down. But at a moderate temperature, if you are doing here, right, the electronic contribution, the contribution coming from electron is decreasing. So actually specific heat when you are discussing the specific heat of the solid, right? Specific heat of the solid, it is the specific heat coming by lattice vibration, specific heat coming from electrons. You are not addressing this because it is very less. Major contribution is from the lattice vibration. For that reason, we are not taking the electronic contribution towards the specific heat. Okay, and you already stated specific heat for gases, and there are two types of specific heat. What is those two? Specific heat at constant volume, constant pressure, that is known as Cp, and specific heat at a constant volume. And Cp is always greater than Cv, and Cp minus Cv is equal to R for 1 mole of gas. But if you do for solids, right, that we have done already in gas class. But if you do that for solids also Cp is slightly more than Cv, right? But there is not change in the pressure. Why we go with only one specific heat for solids means we don't have Cp for solids. It is only Cv only. At constant volume, we can think about constant volume means size. Volume means size. Alright? Constant pressure means in gas they are actually moving and they hit the wall. and for that reason there is a pressure coming into picture. But in solids they are not